All right, so we gave everyone a few minutes, so let's get started. Really fast, just to go over a little bit, I'm Rodrigo Aramburu. I'm the CEO and one of the co-founders of BlazingSQL. I'll talk a little bit more about that in a second, but this is a talk hosted by Rapids Academy, and Rapids Academy is basically a collective of different startups that are involved in the Rapids ecosystem. BlazingSQL is one of those startups. Graphistry is one of those startups. And coiled computing is another one of those startups. So Graphistry focuses on graph analytics and graph visualization. Yeah, so Leo actually posted to all attendees a really good link to the Rapids community. Actually, you know what I'm going to do? I'm just going to share my screen and show that link off because it makes a lot of sense. So if I can find the chat, I guess I can't find the chat. I'm going to open up that link first, and then I'll share my screen. So if you want, there's a lot of different contributors that are part of the Rapids Academy, so Anaconda, BlazingSQL, Capital One, Walmart, QuantSight, NVIDIA. Graphistry has put a lot of work into the Rapids Academy. Dask is a big project which Coiled Computing works on, and some of the original contributors to Dask are involved with Coiled Computing. And so really what we're doing is we're just creating an ecosystem to teach users about GPU accelerated data science and analytics, and how it is that you can take workflows that you already run today, but start accelerating them on top of GPUs. So the other quick thing I wanted to mention as well, Rapids Academy, I'll mention this at the end and we'll send out some information, but we have another talk that's already scheduled for August 11th. That talk is specifically going to be around using Dask and multi-GPU, or algorithms that run on multiple GPUs, not just one GPU. And that's going to be led up by Coiled Computing. And yeah, it should be a great webinar. There will be a webinar and a live lab similar to what we did here, or what we're doing here, and what we did at the previous talk when it was GPU security analytics. Okay. So with that, let's get started. So real fast, like I mentioned, I'm Rodrigo. I'm one of the co-founders of BlazingSQL. And BlazingSQL has been this dream of basically trying to figure out how it is that we can use GPUs or graphics cards that have incredibly high performant memory and thousands of processing cores to accelerate SQL processing. So we've actually been working on this problem for about 6 years now. And a little over 2.5 years ago or so, we started working really integrally with NVIDIA and a lot of the team members that are part of the core Rapids team. And we were starting to iterate over an idea of what GPU accelerated data science could look like. How is it that we could work together so that we're all not necessarily trying to reinvent the wheel? And because of that, BlazingSQL is actually the second largest contributor to the Rapids community, particularly a package we'll be talking about during this talk called Kudiaf. And so let's just talk a little bit about what is Rapids and why does it matter. So when we were thinking about Rapids initially, we basically saw that there's a lot of popularity in a variety of different Python packages. They're incredibly easy to use. They're very functional. They make a lot of sense in terms of what it is that you're trying to do. Pandas, for example, is a great example of this. Scikit-learn is another great example of this. But the problem is that scaling these solutions to very large scale data sets is really time consuming, really difficult, and not necessarily possible. Dask is an incredible project, which we'll talk a little bit about Dask later on in the webinar to helping you scale problems up. But we think that there's a more important component, which is processors, accelerators particularly, and in this case, GPUs, right? What if we can take the power of graphics processors, and now we're not just applying them to deep learning, we can be applying them to ETL, we can be applying them to machine learning, we can be applying them to visualization, etc. And so that's what Rapids really focuses on trying to do. So Rapids is a Python ecosystem for being able to do these complete workloads, right, end to end, from raw data to model trained or visualization rendered or what have you that you're trying to do entirely inside GPU memory. And a few key, components about the Rapids ecosystem is one is it's entirely open source. So if you're looking to integrate Rapids, BlazingSQL, etc., you're totally able to do that with it's an Apache v2 license. And yeah, it's very permissive. You're really allowed to do whatever you necessarily want with it. Second is that it's GPU accelerated. So we've already been touching on this, but it leverages graphics processors that have, as I was mentioning, much higher bandwidth memory and thousands of processing cores. So if your problem is easily parallelizable across those processing cores, you can get really, really dramatic performance improvements. And then the third thing is they're really tailored towards data science requirements and the way that data scientists really like to work inside Python today. So many of the APIs inside the Rapids ecosystem do their very best to mirror popular packages inside Python data or PyData ecosystem. And we'll go over a little bit of that in a second. So this is a very generic usage architecture of the different packages and how they interact. But this is actually now not even all-encompassing of what exists inside the Rapids ecosystem. So there are a lot more projects here that aren't listed. Really quickly, just to kind of list these out from left to right. The first two are very much oriented around data preparation. So BlazingSQL is a SQL engine on a data frame, on these Kudiaf data frames, as we'll explain in a second. Kudiaf data frame is effectively just a pandas-like API, but the data frame itself is in Apache Arrow in GPU memory. So it makes it really dramatically more performant. QML is basically scikit-learn, and it's a re-implementation of the API in scikit-learn. QGraph, very similarly to QML, is a re-implementation of NetworkX for graph analytics. And then there's plugins with deep learning frameworks, as well as visualization frameworks based off of our adherence to a variety of standards. But what's really important here is this GPU memory, Apache Arrow columnar data frame. And this is basically the interoperable, movable data frame across the entire ecosystem. So BlazingSQL can run a SQL query on that data frame or a group of data frames. Kudiaf can run pandas-like operations on it. QML can pass a Kudiaf for a linear regression, for example, or DB scan, or a variety of different machine learning algorithms, and so on and so forth. So going back to the previous point, actually, just before we go to the next slide, this is all about making Python scale up to terabyte-like workloads. And so we started working on a big data benchmark. And in this big data benchmark, basically what we had is a terabyte of data. That terabyte of data represents a retail customer, a retail schema and database. And they have both on-premise sales, so in stores, but they also have an e-commerce component. So that's what this benchmark generates. It generates a terabyte worth of data for all these different types of workloads. And there are about 30 different workloads. And those workloads come from raw data that we have in Apache Parquet on some sort of storage layer. In this particular case, we used Weka, which is high performance remote storage. If you're not familiar with it, weka.io. And what we did with that is we connected it to a GPU node and started running these workloads. And like I was mentioning, these workloads, they have SQL, they have Pandas style data frame manipulations, they have QML for machine learning work, they have sentiment analysis, there's text analysis where we use Spacey. So there's a lot of different things that are happening across these workloads. And I just grabbed a few of them. I grabbed 5. They're not the 5 best. I actually grabbed the 2 worst that we had, the 2 best queries that we had, and one just middle of the road. And what's really impressive is the current winner for the 1 terabyte data set is this Huawei configuration with Cloudera. And we basically put our times against theirs. So they're the times in green. This is log scale. and ours are the times in purple. And we ran our same problem, but we ran it on a single DGX1 server. So for anyone who's not familiar with this, this is a GPU server from NVIDIA that has 8 V100 GPUs. So that's about 256 gigabytes of video memory. And so even though our server actually cost quite a bit less than the Huawei configuration, so over 2 times cheaper, we on average ran about 44 times faster. And that's really what the promise is of this entire Rapids ecosystem, is that in just very basic, straightforward Python, I'm able to run these sort of workloads at scale and more cost effectively. In fact, just to kind of show off what those workloads look like, this is entirely open source, the work that's been done for TPCx-BB with the Rapids AI ecosystem. So you can find it inside the Rapids AI GitHub. Maybe someone from the panelists can actually share that information in the Slack or the QA, or the chat, I mean. But yeah, you're able to jump into this and you can actually see all of these workloads. So let's see, for example, query 28 was one of the queries where we got a really large performance improvement. And so let's just see what that looks like. So here we go. So as you can see, we're bringing in a bunch of different, projects, CuPy, which is very similar to NumPy, Dask. We're bringing in, let's go down to the workload itself. We'll just look at this really quickly because we've got a lot of other stuff to go over. So basically what you see, right, is we're building these features, we're building these labels, we're running these models, we're running predictions, and all of the ETL kind of component happens down here with a series of different queries that are submitted to this terabyte data set. So we're doing sorts, we're doing where clauses. So this is a pretty simple project kind of query, but then there's, as you can see, a variety of different machine learning steps that happen on top of this utilizing QML, which really does everything it can to mirror the scikit-learn API for these workloads. So jumping back, let me present again. So that's what we were saying, right? What if we could make Python, scale up to these terabyte terabyte-like workloads? And if you notice, right, many of these are coming in under 10 seconds. So these workloads become interactive processes. It's not like we're sending them off for almost 1,000 seconds, or hundreds of seconds, and then coming back to them to see how well they ran and what happened. We can be interactively running these complete workloads inside of our notebook. So that's really exciting. So the bread and butter of the Rapids ecosystem was really having a solid strategy around the data frame, because the data frame is basically the interoperable object. It's the thing that you can send around to the rest of the ecosystem so that other projects can actually make use of it. Because what's the point of transforming a bunch of data if there's nothing to necessarily do with it afterwards? And so the first and really important one to talk about is Kudiaf. And Kudiaf, really, the easiest way to think about it is, as the title says, it's pandas on GPUs. So if you have any familiarity with pandas, you'd notice right off the bat that this is very similar to pandas.read_csv. We just pass in a file path, and that outputs that reads in a data frame. And so this is a relatively small one. It's just shy of about 1 million rows, but it comes in under a second of reading that CSV locally into GPU memory. So that's pretty fast. If we're talking about what kind of speed up expectations you can have versus pandas, they're really quite intense. I believe that this is a comparison of a DGX2 with 2 Intel cores on. I believe that's something. Excuse me, a DGX1. So it's about 8 GPUs with comparison to I think two Intel Xeon processors. So server class hyperscaler style processors. But even then, right, you're able to get really intense performance improvements. And it's just because the GPU is that much more effective at running a lot of these distributable algorithms. And so that's what Kudiaf is like. It's providing this pandas-like data frame that you can do all sorts of pandas manipulations to it, but entirely inside GPU. And so where Blazing kind of takes that to another level is Blazing lets you run SQL queries. So a lot of people love pandas. Pandas makes a ton of sense. And we actually think that there's a place for utilizing both pandas and SQL on a particular data frame to create, holistic complex workloads. And in this particular case, we're showing the most basic usage of BlazingSQL, which is literally just running a SQL query on an actual data frame that lives inside GPU memory. And so at the end of the day, when BlazingSQL runs a query, everything becomes one of these Kudiafs, one of these data frames. So what this enables us to do is, one, we're able to share a lot of the code with Kudiaf. So we have low-level C++ primitives for doing all these different types of these merge operations, these sorts, group bys, aggregations, etc. in C++ inside what's called libkudiaf, which is a C++ library that we all work off of. And what that means is, as a community, if you make one of those kernels faster, then the SQL query that will be calling that kernel will also get faster. And so in this particular case, like I was saying, everything becomes a data frame before it becomes before BlazingSQL processes it. In this case, we pre-made this data frame. We can also, just as easily write this create table, and instead of passing a data frame, we can pass in a file path here. And what literally will happen underneath the hood is the create table statement will be running this .read CSV function effectively, or the libkudiaf layer, the C++ layer of this function. And that way, if someone creates a new file reader for Kudiaf, let's say before we didn't have orc support, so Apache orc, if you're familiar, distributed data format. Someone created a PR that let us read orc files, and because of that, we could then start running SQL queries entirely off of orc files. A few key features. So BlazingSQL, while it is not SQL complete, it is compliant. So we don't break any of the norms. We don't make anything unique with regards to our particular SQL. We actually utilize an open source parser called Apache Calcite. So we follow a lot of standards, and if you write, clean SQL, we can take quite a few flavors of it and actually turn that. What basically happens is we convert that to libkudiaf function calls, which is how we get this. The second thing that's really interesting with BlazingSQL specifically, we have out-of-core processing. I'll talk about that a little bit on the next slide, but it enables us to run queries on data sets that are larger than GPU memory, don't fit into GPU memory. And I'll describe a little bit about how that works. And I'll be showing this off very briefly before the end of the webinar portion and more in detail during the lab portion. We support storage plugins, and what storage plugins let you do, if you're familiar with things like Apache Drill or Presto, we let users very easily run or connect remote storage sources. So maybe you have a bunch of Apache Parquet files on AWS S3 or Google Cloud Storage. You can register one of those storage systems with the Blazing context is what we call it. We'll show that off a little bit. And when you do that, you can basically point to files or directories that live inside those storage systems. So talking a little bit about out of core, this is actually an incredibly recent feature. We just deployed this in version 0.14 stable. So that came out, if I'm not mistaken, maybe three or so weeks ago. And what this basically lets us do is whenever we get a SQL query, we create a relational algebra plan or an execution plan. And that execution plan has a variety of different compute kernels that have to happen. And what we've created is it's basically a directed graph that has, for every kernel, there is a caching step that can exist, or a caching node that can exist in between each of those operations. And so these caches are really quite extensible. Right now, we support 3 different cache machines, as we call them. One of them is GPU memory. The second one is system memory. And the third one is local disk, or any disk that, POSIX, right? Anything that just looks like a disk. So remote storage can also work as a caching layer. And very soon, we'll be adding more potential cache machines. You can think of things like AWS S3 or Google Cloud Storage or Azure Blob as also being caching layers. So if queries start really blowing up, beyond the expectation of what the SQL query, or beyond what the GPU, available GPU memory, system memory, or even local disk space can handle, then we'll be able to blow up, create temporary tables effectively on AWS S3 and other things. But that hasn't been, those remote storage plugins haven't been built into the cache machines. Right now, it's system memory, it's disk, and it's GPU memory. Cool. Oh, and we don't have numbers coming out on this yet, but we're actually working on it right now. This out-of-core processing has proven itself really, really scalable. Right now, the limit we've got into is about 10 terabytes. So a 10 terabyte data set. We actually did that TPCx-BB benchmark that we were talking about before at 10 terabytes with one GPU. So one 32 gigabyte GPU running the queries, the machine learning, the sentiment analysis, et cetera, on a 10 terabyte data set. And it's really BlazingSQL's capability of its out-of-core and the ETL step, which is the step that actually has to read, those 10 terabytes of data, that makes that so effective. We can run, out of the 30 workloads right now, we can run 22 workloads, if I'm not mistaken. We might have added a couple of those in the last day, 22 out of 30. And that's just because out-of-core, like I was mentioning, it just got released and stable just a few weeks ago. And so we're still, sussing out edge cases, but it's really proving itself really scalable. 10 terabytes with a single GPU is pretty wild. And then where things really get interesting is what happens if you want more than one GPU and you're trying to actually operate on data frames that just would never fit in a single GPU memory, and you need to do different things with them. And so this is where Dask comes in. So for anyone who's not familiar with Dask, it's a really impressive project. Dask's objective is to natively scale Python. So you can think of it as, a really kind of advanced scheduler that creates DAG, a directed acyclic graph of operations. And you can kind of wrap it around different Python functions that you've built out. A really interesting implementation of that is what's called the Dask data frame. And it was implemented on pandas originally. And so you can think about it, you have a bunch of pandas partitions or pandas data frames across a variety of machines, and Dask creates an abstraction for a Dask data frame that is all those data frames. And where we took this in the Rapids ecosystem is we created a thing called Dask Kudiaf. And it's the same exact idea, right, where you have these partitions of Kudiafs, and then there's an abstraction on top of it that is the Dask Kudiaf that you can operate with. And this is a huge kind of component of the Rapids ecosystem because this is how we handle distributed data frames across, multiple GPUs or even multiple servers. And Blazing kind of takes that to another level in that BlazingSQL, when it's running on multiple GPUs, it utilizes Dask and Dask's awareness of all the GPUs and all the servers to basically create a distributed BlazingSQL cluster. And so Dask will actually, launch independent BlazingSQL workers on every GPU in a particular cluster. And really all we have to do is pass one of these Dask clients is what they called. It's the client that manages, the scheduler that then reaches out to the workers. And if we pass that inside Blazing, and I'll show that off. Will I show that off? I might not show that off. We'll definitely be showing it off at the next talk though. Then BlazingSQL will start running in distributed mode across all the GPUs that Dask is aware of. And a result set that gets returned from BlazingSQL in one of these conditions is no longer, so BlazingSQL, when it runs a query, it returns a Kudiaf. In this particular instance, when it's multi-GPU or multi-node, it'll return a Dask Kudiaf. And so that's like the main difference with BlazingSQL distributed and not distributed is instead of getting a Kudiaf, you get a Dask Kudiaf. But that's great because it plugs into the rest of the Rapids ecosystem. So you can keep doing ETL with Dask Kudiaf, or you can pass one of these Dask Kudiaf, data frames to Dask QML, which basically just takes all the QML work, the machine learning, scikit-learn style packages, and distributes that across, however many GPUs you might have, etc. So going a little bit further, so machine learning on GPUs, we talked a lot about ETL, and we're obviously going to be a little bit ETL centric since I represent BlazingSQL, and that's the part of that I dedicate the majority of my time to. But we wanted to talk a little bit about a few of the different other packages that are available inside Rapids and how things kind of come together. And QML is machine learning on GPUs. And so very similarly to how, we are talking about pandas on GPUs, this is machine learning on those same data frames, also on GPUs. And where it gets really interesting is it really does its best job to mirror the scikit-learn API. It does a really good job about that. This red text here, if I literally just change this out for scikit-learn, this code would run. I mean, assuming I had the data and everything already generated. But this code would effectively run. That's literally how simple of a difference it is. But this is running on GPUs. This actual DB scan was running on GPUs. And this is really, you can get really impressive performance improvements. There's a lot of different numbers that NVIDIA posts about all of these. So I recommend you go check them out. But, 10x, 50x, 100x, these are not, obscene numbers to see in terms of the machine learning acceleration. And so if you take, all the acceleration you get on the ETL side, and then you have it on this machine learning side, and you have a shared data frame that's never copied, that's never serialized as it's passed from one package to another. It's literally just, sharing the pointers of this object. You can have really high performance workloads, and all of it can be running off of, this X right here, this is a Kudiaf. This is a Kudiaf data frame, right? That's how powerful these things really get. Just real fast to kind of go over, there's a lot of different algorithms that are supported. And so we'll be sharing these slides so you'll have access to this information yourself. But, there's logistic regression, KNN, SVMs, random forest, k-means. I'm not going to read through all of them, UMAP, principal component analysis. There's a lot of different library or algorithms that have been implemented in QML, and you can really start getting pretty impressive performance improvements just by looking into QML, what's going on, and using it alongside Kudiaf. We're just going to jump forward a little bit now and go straight into data visualization. So I'll be showing this off during the lab portion, but one of the things that's really, really cool about the standards and the adherence to standards inside the Rapids ecosystem is how effectively and how quickly different visualization platforms have been able to figure out ways of integrating with the Rapids ecosystem. So one thing that's great is because Kudiaf mirrors pandas so much, there's actually a great function, and we'll be showing that off a little bit in the lab portion, that's .2pandas. And once you do .2pandas, a Kudiaf is converted into a pandas data frame. And so if you want to run a visualization with matplotlib or Seaborn, et cetera, you can just pass it that pandas data frame now, as if you were writing pandas all along. And really, you did all of your ETL work and all the heavy lifting on the GPU, and you just did that last mile, right? That last bit to pass it over to a bunch of different visualization platforms you already know and love, assuming that they support pandas. But if you want something that's actually GPU accelerated on the visualization side, which when it comes to rendering, millions of points, that can start becoming pretty important. There's a variety of different really great projects. One of our favorites to use is actually Data Shader. So Data Shader doesn't just support the ability to take a Kudiaf. We can actually pass it a Dask Kudiaf. So when we're running distributed on multiple GPUs, and maybe we have 500 gigabytes of data that we're pruning through and trying to pass millions or billions of points to a visualization renderer, Data Shader does a really great job of taking that Dask Kudiaf. Plotly Dash has also integrated Kudiaf so that you can build visualizations if you're a fan of Plotly. And a Rapids internal project for dashboarding that's built off a variety of different tools is called QXFilter. And this is also a really great tool for doing dashboarding. And we'll show off a couple of examples in the lab portion. So real quick, I'm just checking the time. Yep, we're doing well in time. So I'm just going to jump into basically what is a hosted Jupyter Lab environment. And so this is called BlazingSQL Notebooks. And I'll be sharing this this repo later or after the class that I'm going to show right now. But you're all more than welcome to actually jump into BlazingSQL Notebooks. It's at app.blazingsql.com. You need a Google login to get in. But what BlazingSQL Notebooks does is it gives you a private Jupyter Lab environment, but you're running on shared resources with other users. So we're actually, there's a variety of servers that I've stood up that we're all going to be able to jump in during the lab portion, but the actual GPUs, the system memory, the CPUs and everything are shared resources, but you have your own private Unix user with your own environment, with your own, files, folders, directories, etc., whatever it is that you want. And one of the cool things about this environment is that we've put in what's called the GPU dashboard. So let me just move some things around. And this GPU dashboard gives you a lot of information on how the GPU is being utilized, and you can see, if there's memory and so on and so forth. So I'm just going to run a quick out-of-core demo. I just want to show how out-of-core works. So right now, this is running on a Tesla T4, and the Tesla T4 actually isn't empty. It already is using, I can't really tell, like 3.7 gigs, 4 gigs worth of memory. So we have a 100 gigabyte data set that we're going to be running queries, a few different queries on. So to get started, the way that you start BlazingSQL is you create one of these Blazing contexts. And so basically with this Blazing context, I can now, I should have probably restarted this. Okay, we're good. I can now basically run or start running a variety of different BlazingSQL statements. So here what I'm doing is I'm registering a public S3 bucket. So I have a public S3 bucket. It's got a bunch of Apache Parquet files in it. So I'm just going to register it here. And once I've registered it, I can effectively just start pointing towards directories. And these directories have, a bunch of different Parquet files inside of them. I don't have to put a wildcard or anything. It reads this as if it is effectively a wildcard and that this directory is full of all the Parquet files I care about for this table called orders. And so I'm just going to run this real fast. And this is about 100 gigabytes of data. And so what BlazingSQL is going to do now, you'll see that it's starting to tick up. And basically, it's reading the metadata from all these different Parquet files across all these different directories. And it's creating a scheme awareness so that we can run queries off of it. And we can refer to the columns by name, and we can refer to the tables by name as well. And so since Apache Parquet is self-describing, it basically has all of that information. So it's going to take a few more seconds, and then there we go. That's all it took, right? So if you have a 100 gigabyte data set and you want to get started with BlazingSQL today, this is literally all you have to do, right? You just come in, create a notebook, right? You can create one of these notebooks. We support Rapid Stable and Rapid Nightly, so you can get the latest and greatest that gets built every night off of the nightly, assuming it passed a few checks. If it doesn't, we wait till the next day, and so on and so forth. But you can just, register an S3 bucket. If you have, if it's not a public bucket, you can register the access key, secret key, etc. You can even choose encryption, etc. But now that's all you have to do. You just point the SQL engine to those files, and now BlazingSQL is totally aware. So if we grab a query like this, I'm going to start running it while I describe it. Here, we're bringing in 3 different tables, and we're doing 3 different joins. This is a 600 million row table. This is, I think, like a 200 million row table. This is, I think, 150 million row table. So pretty big tables. We're taking out a few different columns. We're doing, some where clauses. We're doing some group bys. We're doing an order by. And mind you, all of this is happening on a single GPU. Before, when we were doing 100 gigabyte, demonstrations, we would have to have 100 gigabytes of GPU memory. So we'd probably be running this, on 6 to 8 of these different devices, depending on how much we necessarily needed. And there you go. You could see all this activity in GPU memory. It was doing all sorts of stuff. And then it finished the query. And there we go. That query returned to us in about 38 seconds. So 100 gigabytes of data, 1 GPU, and that's how it processed it. We'll do this one. We'll do this one as well. We'll just kick these off real fast. And that way we can look at them after the fact. So here we have another query. Again, it's a nested query now. So this adds a little bit to the complexity. Here, maybe I should zoom in. I just heard that I should zoom in, so hopefully this helps. So you can see, right, there's an internal query with a where clause, and then we're doing a group by and an order by. It's getting really busy. And then there we go, 31 seconds, and we got this. Here, I'm just going to push that away. And we got that result. And then similarly, this is just a single table query. Really all I'm just trying to show off is what happens with the out-of-core processing, right? So here we go, 600 million rows, just a few different where clauses and a sum, and we're able to get this in about 15 seconds. And so you can even notice that the CPU memory is actually going up a little bit, and that's because it's caching on the system memory as it's running these different queries. So this is a big one. Oh man, I don't even know how long this one takes. I think I ran this before in about 30 some odd seconds, but we're bringing in a ton of different tables. You can see this is all just standard SQL. Nothing out here should be out of the ordinary if you're familiar with SQL. And in the interest of time, okay, there it came out. You know, we can see this running in about 39 seconds. So this basically brought in all 100 gigabytes of data. It's important to note that while we do support things like predicate pushdown, so like the Apache Parquet data has metadata that we can leverage for the where clauses, for example, so we don't have to bring everything in. The benchmark we have right here, which is called TPCh, everything's basically randomly distributed. And so the metadata doesn't really help. So we really are doing just like full scans of the data for most of these. Maybe there's like a Parquet partition that we got lucky in, but in general, it's pretty just randomly distributed. And so, you know, bringing 100 gigs of data from S3, querying it, and then giving a result set in 39 seconds, it's pretty fast. And there's ways to obviously make it faster, more GPUs, faster storage solutions, etc. So let's go back. So that basically brings us to the end of the first part of the talk. Just real fast to kind of talk about a few different things, right? This is a full open source community, so we're looking for anyone and everyone to please get involved. You can see our GitHub page at BlazingDB. You can also see Rapids AI GitHub page and Dask. All of these, there was a question I saw earlier about contributions. All of these support external contributors, right? There are processes on how you can become an external contributor. So please, you know, check it out, see if there's something that you care about. We're always looking for people that can support the community because there's just so much to really do to make this all work and sing perfectly, and you know the way that we envision it as well, beyond what it does today, which is already quite a bit. You can also follow us on Twitter. Twitter is the place that both Rapids AI and BlazingSQL puts up everything and anything about the latest and greatest of what's going on. So if you want to be up to date on the nightly updates and what's going on there, or the latest benchmarks, etc., we heavily recommend that. You can also check our Medium blog. That's where we talk about a lot of things that are going on. So if you go to blog.blazingdb.com, BlazingDB is a vestige of an old name, but that URL is difficult to change. Unfortunately, that's a whole different story. You can check out that blog, and then Rapids Academy, right? So we're hosting this whole thing underneath the Rapids Academy name. Learnrapids.com is the website. And we're going to have a talk August 11th, as I was mentioning at the top of this talk. We're going to have a new talk on multi-GPU and Dask, or using Dask Kudiaf specifically, on August 11th at the same time, 11 a.m. So please check that out. You can check it out on the website, learnrapids.com. There'll be an Eventbrite coming out very soon, and we'll also be sending out an email to everyone. Real fast, just to get started. So Anaconda, everything is installable via Conda. So if you have a GPU in a laptop, in some sort of server, in a desktop, what have you, and it's a supported GPU, that means it has to be NVIDIA, and it needs to be what's called Pascal plus architecture. So that's, you know, for consumer grade cards, that's 10 series and above. You can Conda install this in Ubuntu and get up and running on your own environment. If you want a pre-set up environment, BlazingSQL Notebooks offers that with a Tesla T4. It's at app.blazingsql.com. And actually, in a few weeks, we're going to be releasing a beta to the ability to create fully private, dedicated, you know, no shared resources, JupyterLab clusters with more than one GPU. So you can basically get started in a matter of, you know, a couple of minutes running multi-terabyte queries utilizing BlazingSQL Notebooks. And then we're also fully deployable in the AWS Marketplace. You can get the full AWS stack. All the versions are pinned, so they're made to work together, and they're available. So real fast, I wanted to open up this time for questions. So I know that there's a few different questions that have been asked in the Q&A, and there might have been questions in the Slack. So I'm just going to look at those real fast and see if I can answer. If you do have any questions, please submit to the Q&A portion of the Zoom if you're inside the Zoom. If not, you can do it in the Rapids Academy Slack, and I'll just try to go through these and answer them as best I can.